Hello everyone. So we'll have another example on the determination of the bearing capacity under a shallow foundation. This time we will consider other factors aside from the normal bearing capacity factors. We'll have to consider the shape, depth, and inclination factors. In this example, we are given a square footing with a section of 1.2 meters by 1.2 meters. The soil parameters are given as follows. We have the dry unit weight of 16 kilonewton per cubic meter. So the soil is cohesionless and C prime is equal to 0. And the angle of friction is equals 32 degrees. The groundwater table is located 0.5 meters below the ground surface. So this is 0.5 meters. And the depth of the foundation is 1. Df is 1. It's 1 meter. And therefore, this is 0.5 meters as well. Below the groundwater table, the saturated unit weight is given to be 19.5 kilonewton per cubic meter. And from this given, we are asked to determine the safe gross load. This one, that is a safe gross load, and we denote that as capital Q because the bearing capacity is a small q. So this could be in kilonewton or in newton. So let's have it in kilonewton. A given factor of safety, which is equal to 3, is still the typical factor of safety for a foundation. So what is the gross load that the foundation can carry? And in this problem also, the loading is just vertical and our inclination factor would be just equal to 1. So from the given data, we'll be using the Meyerhoff's modified bearing capacity equation, or the general bearing capacity equation, sometimes called, which considers some factors like the shape factor, the depth factors, and the inclination factors. So we'll have additional factors that will be included in the formula. But since our cohesion is 0, from the general formula, we can eliminate the first term of the equation, the C times N sub C. And since this is a vertical loading only, we have the factors F sub Ci, which is equal to F sub Qi, and also that it will be equal to F sub gamma I. And since that is vertical loading, these factors will just be equal to 1. This is for vertical loading. Okay. If we'll be using the formula, the modified bearing capacity, The formula states that Q sub U is equal to C times NC, but we'll not write the formula, that term anymore, because that becomes 0. So we'll have plus Q N sub Q, and with the addition of the shape factor, so this becomes Q sub S multiplied by F Q sub D, or the depth factors, and the inclination factor is just 1. So plus we have 1/2 of gamma times B, and gamma times the shape factor for this term multiplied by the depth factor for this term. So that's the formula that we're going to use. And let's look at the formula. If most of the parameters are given, so Q will be calculated first, N sub Q and sub gamma can be obtained since we are given the angle of friction, and the rest of the parameters, for the factors rather, shape and depth, can be calculated based on some formulas. B is given, and the unit weight will be based on, this gamma will be based on the location of our water table. So let's begin getting the values of the bearing capacity factors from our angle of friction, from our given angle of friction of 32 degrees. And this time we'll be using the table provided by or modified by Meyerhoff, and from that table, given an angle of friction of 32, our N sub Q, or the effective stress, is equal to 23.18. You can check that from our book. And our N sub gamma is 30.22. Again, the table that you're going to use is the modified one and not the Tersagi's bearing capacity equation. Okay, then the other factors such as shape and depth factors can be calculated. Let's begin calculating the F sub Q sub S. This is equal to, from our table, also from the formula, we have 1 plus B over L. This is tangent phi. B is the width and L is the length, and we have a square section. So this is 1 plus 1.2 as our width, and the length is also 1.2, multiplied by the tangent of, the angle of friction, which is 32, and that can be equated to 1.625. Next, we have F sub QD. Our formula is 1 plus 2 tangent phi prime, 1 plus sine phi prime, square d sub f over p, and all the terms are known, so we can just plug in the values. Plus 2 tangent 32 degrees, 1 plus sine of 32, and this is square, multiplied by our df is 1.0, divided by the width of the foundation, which is 1.2. And the F sub QD is calculated as 1.23. Then we have F sub, here we have F sub gamma S, which is equivalent to 1 minus zero point 0.4. That's again from the table, B over L. So these terms, all the terms are given. 0.4, the width of the foundation is 1.2, and the length is also 1.2. So we have 0.6 here. And then we have F sub gamma D, which is equal to 1. So most of the terms are already known. We can just calculate the effective stress, or Q, or the overburden pressure, and then at the bottom of the foundation. So from here, to get the Q here in this portion, we start from the ground surface. So for the dry condition, the water table is located 0.5 below the ground surface, and so the upper portion is considered partially saturated or dry, and so we use 16 as our unit weight for that part. So we have 0.5 meters multiplied by the unit weight of 16. Okay, and below the groundwater table, we will use a submerged unit weight, and that is obtained by our gamma sat, or gamma saturated, minus 9.81, and our gamma saturated is 19.5 minus 9.81. So from here, our effective stress is 12.845 kilonewton per cubic square meter rather. So that is our overburden pressure. Then I guess all the parameters in the equations are already known, so we can just plug in the values to solve first for the bearing capacity before we can solve for the gross load. So the bearing capacity would be equal to the effective stress of 12.845 multiplied by N sub Q, which is 23.18, multiplied by F sub QS, which is 1.625. Then we have F sub QD of 1.23. Then we add the next term, which is 1/2 of gamma. So what gamma are we going to use? What unit weight? For this case, I think this is case 1, right? Case 1, the location of the water table is within our D sub F. So if that is within our D sub F, we will use the gamma submerged, or the effective unit weight, or the submerged unit weight. And we can solve that by our gamma sat, or saturated unit weight, minus 9.81. So we'll have 9.5 minus 9.81 for our gamma. Then we have B, which is equal to 1.2. Then our N sub gamma is 30.22. And then we have F sub gamma S, which is 0.6. And then our F sub QD, or F sub gamma D rather, is 1. So with this, we can calculate for our Q sub U, or the bearing capacity, which is equivalent to 700.54. This is in kilopascal, or kilonewton per square meter. But what we want is the load Q here, which is applied on our footing. And to do that, we'll Oh, we'll get first the allowable. We'll get first the allowable bearing capacity, which is equivalent to Q sub U divided by the factor of safety, and that would be equal to 700.54 divided by 3, and our Q allowable or allowable bearing capacity is 233.51 kilonewton per square meter. Therefore, to determine the allowable gross load, Q, that is equal to Q allowable multiplied by our B square. And that would be equal to 233.51 multiplied by 1.2 by 1.2. And our Q is calculated as 336. This is in kilonewton. Okay, this is our final answer. Thank you.